Hello, high school astronomy students. Here's Mr. Z for probably our final lesson of the year. Hopefully that this finds you well and ready to enjoy your summer. Drake's equation. This has been requested by one of your teachers that we end the year with a Drake's equation kind of explanation. As you know, I've mentioned in class several times, I'm an alien fiend. Love the thought of aliens. It's one of the things that draws me into astronomy and keeps me just intrigued about astronomy, is eventually finding other life out there in the universe. And this is along that line. Now this looks like a lot of letters, a long formula equation here, but don't be fearful of it. I'm not trying to teach you new math here, because that's actually not what the Drake equation is about. We call it an equation because it's structured like an equation. But it's not. This is an equation that will never get solved. It's just an organization of thought. Let me explain what I mean. The Drake's equation is after to do one thing. It's a way to organize our thoughts to figure out the number of civilizations that can communicate with us in our galaxy. So this equation just organizes bits and pieces of information that we need to figure out, or at least try to achieve, reach for, in order to finally answer that question: are we alone in our galaxy? All right, so number of civilizations that could communicate with us in our Milky Way. That's what we're after. How many of the civilizations are out there? All right, so the rest of these variables will just be aspects that we need to think about, aspects that we need to study to find more about in order to eventually answer this question better and better. I'm already going to tell you, there's many of this we don't know. There's a lot of guesses here. But as I said, it's not supposed to be solved. It's just supposed to organize our thoughts, organize our process to help us focus where we need to learn this. So let's start with the first one, and that's the rate of stars are born. If stars form very slowly, then all these other factors will happen less. If stars form very quickly, then all these factors happen faster. So to start the equation, we of course have to start with how fast stars are born. All right, now the good thing is we've been studying stars long enough now that we have a good idea of this number. There's still a range, but it's a very small range. We have a pretty good idea of how fast stars form. So the rate at which stars form per year, that's our first thing. If stars form fast, all of this will happen faster. Now, once you form a star, you have to know if that star is going to form planets. So this is the fraction of stars, FP here, is the fraction of stars that form planets. Now, this is another data point we happen to know a lot about, because we're starting to realize most stars come with planets. They're just a byproduct of making a star. So this is also a pretty high fraction, and another one that we happen to know a pretty good estimate for, the fraction of stars that form planets. Next is the fraction, or the number of those planets that are in an environmentally friendly position or condition for life. To sum up, which planets are in the Goldilocks zone? Now, using our own solar system for an example, Earth is the only one. The number of planets in the environmentally friendly position is just Earth. Earth is not too close to the sun to evaporate the water. It's not too far from the sun to freeze our water. It's in that perfect Goldilocks zone just right, where water stays in its liquid form, which, as far as we know, is what we need for life. Sort of the catalyst for life is the liquid water. Now you'll notice something is I put planets in quotes here. All right, the reason I put planets in quotes is because when this formula was made, this is how it was worded: the number of planets with environmentally friendly position conditions for life. But back then, they didn't have the thought of moons having life. And so we use planet loosely now. Planets could, in fact, also mean moons. We have moons like Titan. We have moons like Europa. Europa, for example, has a possible liquid ocean, liquid water ocean under its surface. Titan has an atmosphere and does have liquid on it, and thus could harbor life in its own form. And these are moons we're speaking of. So planets, we use the word planets lightly here, the number of planets with environmentally friendly positions and conditions for life. We could also mean moons. All right, going on to the next one. If a planet can form life, does it form life? Now this is the part of the formula where it starts to break down. We do not know these answers. Mostly because we just have very few data points. We have one. Our Earth formed life. Great. So does that mean it's 100% chance that if a planet can form life, it will form life? That's what we don't know. We need more data points. And so there's a lot of estimates. There's some biology, chemistry, all of it put together. Some say it's very rare that life forms. Some says it's very common. They say that life formed as soon as it could on Earth. As soon as the conditions were okay for life, life happened. And so does that lead to the fact that life is inevitable when it's possible? If it is, then this fraction is very high. If it does take a certain absolute, very rare combination of events, then the fraction is very low. So we don't know much about it. But again, this equation is not about solving it. It's just about organizing what needs to be studied in order to just learn a little bit more. So we need to know, out of the planets that do form in the habitable zone, how many of those actually form life. And now, in order to communicate with us, they need to be able to talk. So those planets that do form life, how many of them evolved to be intelligent, the ability to speak? All right, so if you take a look at our own planet, yes, of course, we got humans that can speak. It's probably the most intelligent. But you got communication between other species, but it's still, when you look at all the species and who can communicate, it's not that many. So our fraction would be very low of how much life evolves to be intelligent. So this fraction is probably going to remain quite low. Now think about that. So only the life that's intelligent can then evolve, or can then create the technology to communicate. So even if there is a faraway civilization that has learned to talk, is intelligent enough to communicate, are they intelligent enough, or are they evolved enough, or maybe advanced enough to create the communication, the technology to communicate? The best example here is radio telescopes. We have been sending radio waves off into space for about 80 years now. So any planet within an 80 light year radius of us could have heard us if they have the proper technology to have received the signal. And so this is an important factor in the thought of this, because if we can't communicate with them, if they're not advanced enough to communicate, then this does hurt this number, or the end number of how many can communicate back. So we need to definitely have this as a factor. They need to have the technology enough to create radio or some sort of technology to receive our radio waves or whatever waves that we eventually will start communicating with. So this is an important factor. Will the intelligent life that does evolve actually have technology or be advanced enough to communicate with us? Last but not least, we do have to take in consideration the lifespan of the civilization. Now, do not think of this as the lifespan of the single human, for example. This is not 80 years for us, for example. This is the lifespan of the civilization. So let's just use humankind for an example. Okay, humankind has been around several thousand years. Now, we've only been communicating for 80 years. All right, so far our L is 80. But how far will that go? How long will we continue to talk and send radio waves and be able to receive radio waves? Now, ideally, this should be forever, right? That we should have this. You would think the humans are smart enough that will adapt to the Earth, will start protecting our Earth so we can stay here as long as possible. And then even when that time comes where we have to leave the Earth, we're ready. We have the Wall-E ship or the Star Trek ships or something like that allows us to just take our civilization, move it into space, and become independent living up there. So ideally, we'd love if lifespan was infinite. Right now, it's only 80. All right, the lifespan, how long we've been communicating in space, our lifespan is only 80. I hope it is infinite, but there's a lot of, when you think of the wars that humans start and environmental issues that humans have to face, it's possible we destroy ourselves before we're able to communicate. And so the shorter our lifespan is, obviously makes it, or the lifespan of any life out there, obviously makes all of this harder to find. Because if they don't live very long, that reduces our possibilities of communicating with them. So hopefully that makes sense, the L. So as you see, this is not solvable. You cannot solve this equation. But trying to solve it organizes our thoughts, organizes and focuses our studies to know what to look for. So real quick, going over the whole thing real quick. All right, so we're looking for the number of communications that can communicate with us in our galaxy. We want to know how fast stars form. How many of those stars form planets? How many of those planets are in the habitable zone in order to have life? How many of those planets that can have life do form life? How much of that life evolves to be intelligent enough to speak? How much of that intelligent life actually advances enough to create the technology to communicate? And how long will that civilization communicate? All of this put together gives us a beautiful a plan into answering the question. Now, even though this is not supposed to be solvable, I do want to throw out some numbers that have been tossed around. Here's the worst case scenario. If you put all pessimistic numbers into the formula, you can see that this is how many civilizations, communicating civilizations, are in the Milky Way. You can see that is well lower than the answer 1. So if this is true, we are alone in our galaxy. All right. Now let's look at the optimistic. If we put only the highest estimated numbers in all of them, then we are definitely not alone. 15.6 million other civilizations are out there ready to talk to us. We just have to find them. All right, so you can see this can go a lot of ways. And again, this is not supposed to be solved. I'm not saying that this one's better than the other one. It's just a way to organize thought. If anything, the difference between these two numbers just tells you how unsolvable this equation really is. It's just an idea to organize our thoughts. So one idea I do want to kind of leave you here with several things. First, here's the middle. If you're wondering sort of where the middle would be, there you are. And so if we take the middle estimate of all the answers, we actually still end up with us being alone in the galaxy. But I don't want you to be discouraged with that. So even let's just pretend for a second it's the middle. This is where we're at. So we're alone in the galaxy. But let's not forget that we have 1 trillion galaxies out there. And so when you take this number and multiply by 1 trillion, that in the universe, there are about 14 million communicative civilizations. All right. So again, that's taking the middle numbers. And again, it could be lower, it could be higher. We're just playing with ideas with this equation. That's all this is. But the key here is, if you remember from the beginning, it's how many, or remember what N stands for, it's how many communicating civilizations in our galaxy. Then just remember how many galaxies are out there, and you can see how much life is out there in the universe. All right. Now, just on a personal note, with my own studies of aliens and such, I'm actually not too interested in those two factors. This would be the factor of, does life evolve to be intelligent, and does the intelligent life advance enough to start communicating with technology? Those two don't interest me. I personally just want to find out, is there life on other planets? Even if it's fish, plants, bacteria, just maybe even little walking around little mammals or four-legged creatures of some sort. That's what I care about. So to me, these are my favorite. These are my important factors. I do need to know, do stars form fast enough to make this all happen faster? Do planets form stars? Are some of the planets in habitable zones around their stars? And then, if they're inhabitable, does life form if it can, and then just like how long it lives. But you only need this to communicate with them. I'm just interested in is something else out there? Is life out there? Is there a flock of birds flying somewhere on some other planet? Is there a school of fish swimming under some ocean in another moon or planet? So these two, just again, personally, just don't really interest me too much. I mean, obviously, if we end up talking to them, holy cow, I'd be blown away. But really, this is the one that matters to me. I want to know, is there just life, just creatures out there in the universe? So that's just a quick overview of the Drake's equation. Again, not solvable, just an organization of thought. And hopefully a lot of these, there's a certain variable here that just latched on to you and you got interested in to know, wow, is life going to form if it can? What's the probability of life evolving to be intelligent? So hopefully something here just sparked a curiosity and you enjoyed this little quick session about the Drake's equation. So like I said, we're here at the end of the year. So this is Mr. Z signing off for the year. I hope you guys enjoyed our labs that we've done. And it was a pleasure working with you guys this year. Hope to see you guys next year. And if you're graduating, congratulations and good luck in the future.